Our next speaker is Professor Arshad from University of Sains, Malaysia, and his title is Intelligent Swarm Underwater Robotics for Coastal and Shallow Water Applications. Professor Arshad, this is your stage.
Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Very good morning. I'm Rizal from University Sains Malaysia. So this is a short table content of what I'll be talking about. So firstly, I would like to thank the organizer for inviting me to the conference to share what we've done so far. So this group has been around since we started the group back in year 2000. So many students have come and gone and passed through the groups, and we have developed a number of systems for our waters. So this is just a simple overview of our campus in Penang. It's an island in the north part of Peninsula West Malaysia. It's about 4-hour drives from our capital city, Kuala Lumpur. So this is there's a visitor from my colleague from China. This is some snapshot of our lab. So since year 2000, we have been working in 3 domain of themes of research. We work on robotic platform. We've worked on intelligent decision making, or AI, and we work on sensor design. So develop devices. So there's 3-prong kind of approach. So among others, we were looking on in terms of approaching the supervisory-based system and totally semi and fully autonomous system, and also hybrid system. So in this case, we work on localization, intelligent sensors and modules, meaning, for example, we have developed MEMS-based acoustic sensors to measure flow, for example. So just to explore, as we know, acoustic sensors are very, it's a dimension-based kind of sensors. When you explore MEMS-based, it's very challenging how you to match the size and the wavelength, the wavelength of the signal. So we work on artificial swarm intelligence. Nowadays, for the past, I would say 4 or 5 years, we've worked on swarm intelligence, developing low-cost platform. Really means, say, low cost is price, because as we know, marine modules are very expensive. Initial navigation system, very expensive. DVL, those are very sensitive stuff. And how do I say it? We want to see a democratization of these products. It's so expensive for us to use. So that's why our team has spent the last 2 decades developing our own modules. We reference to the standard modules that we have in the market. So, and we also develop work on smart power generation and management. As you know, when you deploy system for long-term deployment, you talk about smart power management, because you cannot easily replace the batteries as you like. So you have to know how to extend the lifetime of the platform. So before that, I might have a bit stressed myself in terms of slides. There's so many slides, so I will just skip. And I will slide some of it, almost most of it. So I will just focus on some of the main points I would like to share. So, so the title is about swarm intelligence, and there's I will share some about 5 of the work that we've done for the past 10 years we've done, just to share a glimpse of what we've done, to give an idea. So this is Malaysia. So as you see, this is West Malaysia, this is East Malaysia, and this is, we are surrounded by Indonesia. You have Singapore here, Thailand, Vietnam here, and China, of course, Philippines. So it's very crowded area. It's very crowded, and we have a very busy Malacca Strait here, where every day you have around 100 to 200 ships plying the route. Very difficult to deploy any system here, because you deploy it today, tomorrow you cannot find your vehicle anymore, because so busy, so many economic activities. So they're very difficult to ensure that you can get back your vehicle. And for example, here the Malacca Strait, the average depth is around 50 meters, I think at most we've done the mapping around 90 meters. That's the maximum depth. That's why every time submarine fly this route, they always have to go on the surface, because there's no, as far as I know, there's no acoustic-based modeling for mapping here, and you can get stuck underwater if you go down there. So, and it's very muddy. It's very shallow compared to the bigger oceans, as mentioned by Prof. Jones. I think the average depth is about 4,000 meters. So this is nothing. It's shallow. So we have in Malaysia, because Malaysia is considered a maritime nation, because we have our land area is much bigger than our sea area is bigger than our land area. So you can see the number of applications that we are aiming for. So for us, our group, we have been focusing on environmental and science. Of course, we never, not military, and also oil and gas, and a bit on ship hull inspection and ship tank internal inspection. This is what among the application that we've been doing. Of course, there are many more applications, mid-ocean, passive acoustic monitoring, surveillance. But as far, from our experience, we know many of our counterparts in the temperate zones, they have done many research, but sometimes the solutions may not be applicable to our waters because of the temperature difference, because of the dynamics, etc. So there's always a need for fine-tuning of the system if we get it from outside, from different suppliers for different oceans, a kind of the water type of waters that it is calibrated for. So this is an example of application which is we are trying to tackle. So this is one of the port in Penang. So this platform, it is 800-meter width and 1.5 kilometer long. So it's a solid concrete platform, and there's an issue of inspection under the platform. This platform, and the problem with doing this inspection here is that the water level will, at high tide, the tide will, there's two cycle. So you have a very constrained time where you can inspect under here, and sunlight can only reach maybe 2-3 meters, then it's total darkness. So there is a high chance if you put your vehicle under here, it's going to be there. You cannot retrieve it. So it's quite challenging. And the issue with this is that there's the problem with subsumption, or where the land, some problem with the land, the port on the land side. So they were worried on the poles that is supporting the platform. So there is a serious need. So I guess similar problem also happens at other harbors or ports. But it's just for this one, it's very, the access to the underside of the platform is very limited, and you have certain hours of time that is allowable for you to inspect. So it's just an example. So this is the upper part of the platform, is the jetty. Sorry. Okay, sorry about it. And this is another application. This is a marine park monitoring inspection of, sorry, double redundant. It's a marine park monitoring inspection. So in Malaysia, I just like to highlight the issue of coral reefs. In Malaysia, Indonesia, Brunei, that area, we have what we call a coral triangle initiative, because the size of the combined size of coral reef in that area is as big as the reef in Australia. So there's probably if you have not worked with the CTI group, probably KAUST would want to work with the CTI group, because they have been working on coral preservation in the area for a number of years. So in Malaysia, we have around 38 marine parks and similar problems. We use divers to do mapping, and this is one of the which is on the east of Malaysia in Labuan. Labuan is just off the coast of Sabah. Sabah is the northern state on the east of Malaysia, East Malaysia. So this was done using divers, manual kind of, so similar problem as what been mentioned by many of speakers is it's also been we're trying to solve it or partially solve it using robotic solutions. As mentioned by one of the speaker, we want to do persistent monitoring and observation rather than very selected kind of inspection. So one of the, I will briefly go through this. So we develop, as I said, we focus on three main themes, which is on the robotic platform development, the actual platform, on the sensor design, device and utilization of sensors, and also on the intelligent decision algorithm. So this is one of the algorithms that we developed for control for autonomous underwater vehicle for a pole inspection. So basically, this is in Malaysia, we have a very significant amount of the country's budget contributed by the oil and gas industry. We have a national oil company, Petronas. They contributed at least 30–40% of our yearly budget. And we have many oil platform on the east coast of East Malaysia, West Malaysia on the east side. So one of the problems is on the jacket leg inspection of the pole inspection of the oil platform. So we developed some system and some control in order to inspect try to explore what would be the best trajectory plans, or in order to optimize, in order to reduce the time needed in the water, because there is also because of tide, etc. There's also limited amount of time that you can spend underwater. So you need to get the optimum path planning or trajectory planning to acquire the most information. So we explored a number of paths, and this is an example of jacket kind of jacket type that you can have on the oil platform. So we developed some. Now they are using divers. As you imagine, we have around, if I remember correctly, around 200 oil platform, and each oil platform would have at least not many poles. So how many divers you need to inspect every one of them? So there is an urgent need for robotic solution to that. But even if you deploy a robotic solution, you must make it optimum. You cannot just let it be like that. So that is one work that we've done. And from here, we can see that the best path is the path number 5, the path E, that gives the best kind of performance for the inspection. So I'll just skip this one. And then we developed the platform. We developed an underwater gliders. This was back in 2014, but this is the first time we developed it. So this was the challenge with, I know some of you are using underwater gliders, but we've studied sea gliders and the Slocum, etc., which are very unique and it is for deep water. The problem with our waters, it is shallow waters. And as you know, I think most of us have used acoustic module, you have a lot of noise when you use in shallow water because of the like reflection, and you cannot get accurate. So when you use such a bit for imaging, bit for localization, is very problematic when it is shallow. And just side information, in Malaysia, we have snapping shrimp in that region. Snapping shrimp give a very high frequency noise. So if you try to image using a high resolution acoustic signal, you get worse because of the snapping shrimp. So just a side information in terms of the complexity of the shallow waters. And the problem when you use gliders in shallow waters, you cannot use it for long because it keeps pumping because of the shallowness of the water. You need at least 800 or 1,000 meters as an optimum depth of a glider. So we work with how to develop gliders for shallow waters so that you can deploy it for 100 meters and it can glide well. So we realize a lot of issues for gliders, and that doesn't negate the issue of security. When you deploy your gliders, there's a lot of fishermen around there. In the Malacca Strait, it has happened. One of our universities, they deploy a wave glider, not underwater glider, a wave glider, and the Vietnamese fishermen took it home. So So how can you prevent that? Because it's an open water. So those are some of the real challenges when you deploy, when you have overcome the technology problem, you now face with the problem of how to deploy it and get the data without interference from others. So we develop the gliders and we test it, etc. Okay, I just want to skip it. And then we work on docking. We work on docking because when you deploy your underwater gliders or AUV, you want it to be recharged. But you do not want to deploy and retrieve the AUV every so often. So you want it to be able to dock. So we work on underwater docking, and we use a Blue Robotics platform. And basically, it's an image-based kind of guidance, because our presumption is that because of the distance, is a global and local guided or navigation. So as within a certain region, we can switch to image-based, and we develop an algorithm, a visual surveying for docking. So yeah, as you can see, all these are part and parcel to solve a bigger problems of one particular solutions. And this particular case, for realistic deployment of AUV, we must solve the docking problem, because once you solve the docking problem, you solve the recharging problem, you solve the data transfer problem, because you cannot just deploy and take it out and deploy it again, and that negates the benefits of using AUV, because you do not want a mothership. You should be able to send the AUV, get the data, and it should be there without interference ever so often. Okay, so this is we are not as, I really admire my friend from Maki Lab, because they really go to the ocean. We do not have the luxury, so we do many of the tests in our, and now we are only starting to go to the sea. And then we work on this is for swarm, because we work on acoustic source localization. So basically, I agree with Prof. Jones that swarm is the way forward. But if you swarm can only be realizable if you couple it with low-cost system. If the system is very expensive, it doesn't make sense for swarm, because the cost will balloon. So unless we suppress the cost and it is low cost, then we can go for swarm. If not, it's only for the fibrillation. If the cost cannot be reduced. So what we did was we developed this floating buoy. So we developed about 14 of them. And what we use it for, and we have these hydrophones at the bottom. This is and what we did for this is that we want to use it to do source localization. Let's say we test it, put a beacon, sound source at the bed, in the water, and see what's the best algorithm for it to triangulate to the source. So this is the platform that we've developed. And we developed same time, so you can see there's a number of. So the chair is not part of it. The chair is just to ensure that the acoustic sensor is not broken. So nothing to do with it. But so basically, we have developed 14 of it, and we use it as a platform to test and to determine what's the best swarm algorithm for our application. Okay. And lastly, we also develop what we call a Blim system. This is to get an aerial view. So if you follow my presentation now, you can see that we develop an underwater inspection data gathering device. We develop a floating device, and we develop an aerial data gathering device. In this case, we decided to use a Blim. Blim is a helium field device. So basically, this student, this is my previous PhD student. So she developed the Blim system in order to work in collaboration with the floating device. So that means what we would like to do was to capture an event, a temporal and spatial information, getting at the underwater data, surface, and also aerial information together. But one thing that we realized when we developed this is that in terms of, there's a lot of the issue of complexity of synchronization in terms of communication. because the floating device is communicating RF with the flying. The floating device is communicating with acoustically with the gliders. So it doesn't, the speed and delay are different. So there's a lot of quite interesting complexity in terms of how to get it synchronized, all three of them. So this is, okay, this is obviously this is not in the sea because you cannot see this. This is a mosque. It's not in the sea, this is in our campus. We try to test the mosaicing, image mosaicing capability. So you can see the swarm approach can be applied for a different kind of platform. So we have explored applying to floating in the water and also aerial platform. And the reason we use Blim because Blim is easy to control, but the problem with Blim is very prone to wind. That's a problem. So we control the height. So this was so this is the kind of platform. I didn't share it here, but we also built this buoy. For this buoy was intended for marine park protection. So this is so you can see with what we did was we tried to make it into a system. The buoy, the floating craft, the aerial craft, and also the inside the craft in the water. So to us, we have gathered a number of challenging. So I would say in terms of challenges is the design and development of robust water platform for non-linear underwater environment, because the main problem is to develop a reliable model. And I totally agree. If I have the access to finance, I would go for Prof. Maki route, which is testing in the ocean, because then you can really ensure that your model is reliable. Now our model has yet to be properly tested in the water, because once you test in the water, then you know whether your model is robust, is really robust or not. And then in terms of new localization methods are needed for shallow water application, which is less than 30-meter depth. Of course, for 30-meter depth, it's still okay. But the image of the pod I've showed you recently, just now, sorry, is maximum depth is 12 meters. And the problem with that is that if you deploy our vehicle in the water, it's very difficult to localize our platform. And the water is very turbid. That means you cannot see, visually you cannot see the craft. And it's only about maximum 1.5 meter visibility. So that's why localization for such a shallow water column is critical. And then for us, access to good testing facilities and resources for the field testing are critical, because this is our own problem. It's probably not applicable to most of you. And then the availability of reliable energy harvesting module for long-term deployment platform, including smart power management system. As for now, as far as I know, we have not developed ourselves, but people have explored like the wave gliders platform, the Autonomy platform. They utilize the wave. They convert the vertical motion to horizontal motion for propulsion use. But in terms of when you have significant less amount of wave, how do you harvest the energy from the environment? So this is one of the challenges. And then robust terrestrial and underwater communication module with standardized communication protocol for surface and underwater platform networking. So for us, this is when we deploy all the platform together, then we see a lot of problems because the communication protocols are different for aerial and also in the water. And of course, finally, excellent material selection for platform and sensor verification to reduce the effect of biofouling and seawater corrosion. And this is, for us, is critical. I showed to you the buoy. We have put the buoy about 1.5 months in the waters in the backside of the island. After 1.5 months, and we the first day until 1.5 months later, we get daily updates. And after we have hydrophones in the water, after 1.5 months, the hydrophones is fully covered by barnacles because it's very rich environment. So if you put your hydrophones, you leave it. It's not that the hydrophone doesn't work. It's just it cannot work because the barnacle grew on it. So this is a challenge in such a water. And summary, to me, intelligent autonomous platform to a certain degree will remove the need for man on boats and human in the underwater environment. A key issue for the many ocean-related industry sectors. For us, I give an example. When we've engaged one of the oil and gas operators in Malaysia, we proposed a very reliable robotic solution, but at the end, the company said, we still trust human observation. So this trust deficit is something that very difficult to overcome with just excellent technology and beautiful slides. Okay. And then highlight the important roles to play in the baseline studies. In our waters, Malacca Strait, South China Sea, one of the problems is there is no available acoustic baseline data. So probably military guys have it, but the commercial or the scientific community do not have access to any acoustic baseline study. So that means baseline study from the acoustic perspective is one of them, and it is not available. So there's a lot of things that need to be done. And then in terms of data collection, one of my mentor, Prof. Rodney Coates, he said that in life, in ocean, you do three things: measure, monitor, and manage. If you want to do monitor and manage, if you cannot measure, you cannot do it. So always you must be able to do proper measurement. Then we can talk about monitoring and managing the resources. So it boils down to sensors and making sense of data from the sensors. Okay, a bit more. Then it's about last system. Then the issue of assurance, need to prove guidance and avoidance system for all systems. That means this is about navigation. And finally, I would say the advanced or swarm approach for ocean application intelligent decision making is here to assist overall ocean resource management. So I'm sorry for pushing the time. So I hope you have benefited to some extent in my presentation. Okay, thank you very much.